In our previous video, we demonstrated how to create a Vivado design containing multiple AXI GPIO blocks. We also explained how to control these AXI GPIOs in Vitis using the memory mapped I/O concept. In this video, we will take it a step further by explaining how to access and interact with peripherals directly in a Jupyter Notebook. Steps to upload the overlay and driver code. First, you need to prepare the Jupyter environment. Open Jupyter Notebook and create a new folder. Rename it as per your preference. Then upload required files to this new folder. Navigate to the Vivado project folder and locate the HWH file. Upload this file into the newly created folder in Jupyter. Locate the generated bitstream file and upload it to the same folder as well. Ensure that the HWH and bitstream files have the same base name. If needed, rename them to match your desired naming convention. Add the notebook file. Download the provided notebook file from GitHub and upload it to the same directory. Overview of the provided driver code. At the beginning of the code, various modules are imported, including the MMIO module. The overlay class is used to program the programmable logic of the FPGA. The PL side will be programmed with the provided bitstream. This process also utilizes the HWH file to initialize and configure all required PYNQ functions and addresses, enabling you to interact with the design effortlessly. Exploring the overlay attributes. When you place a question mark in front of the overlay object in a Jupyter Notebook, it displays all the available attributes within the loaded overlay. One of the most important sections in the attribute list is IP blocks. This section lists all the connected IP blocks in the design that are accessible to the ARM core. In the example below, the overlay includes 4 AXI GPIOs. Their names and associated classes are listed. Accessing AXI GPIO in PYNQ. In PYNQ, there are several ways to interact with AXI GPIO peripherals. One of the simplest and most convenient is using the AXI GPIO class. AXI GPIO class provides methods for reading, writing, and handling interrupts from external general-purpose peripherals. It allows you to interact with GPIO blocks by referencing their names from the IP blocks that was displayed in the overlay attributes. This class comes with write and read methods. The write method requires 2 parameters. Offset, the address offset of the GPIO register that you want to write into. Value, the data to be written to that register. For an AXI GPIO, the address space offset for channel 1 data register is equal to 0. This means that to access or modify the channel 1 data of an AXI GPIO, you need to perform read and write operations at the base address of the AXI GPIO with an offset of 0. For example, the following code writes a value of 3 to the AXI GPIO 0 data register. This action turns on 2 LEDs connected to the GPIO. Using the read method in the AXI GPIO class. The read method is used to retrieve the current value of a GPIO data register. This is especially useful when you need to monitor or verify the state of connected peripherals. For example, the following simple code, read the AXI GPIO one that is connected to the user DIP switch and returns its value. Memory mapped I/O. The MMIO class allows a Python object to access addresses in the system memory mapped. Using this class, registers and address space of peripherals in the PL can be accessed. Define a MMIO object. To define an MMIO object, you need 2 parameters, the base address of the peripheral you want to access and its address range. Both of these parameters can be found in the Vivado address editor or the HWH file. In the following section of the code, I listed all the AXI GPIO addresses as obtained from the Vivado address editor. The address range for all GPIOs is the same, set to 64K. Using these addresses, I created an MMIO object for each AXI GPIO. The MMIO class provides read and write methods to interact with the peripherals. For example, the following code demonstrates how to send values to an adder implemented in the PL by interfacing with AXI GPIO 2 and AXI GPIO 3, and then reading the calculated value back. Finally, in the last section of the code, we control the user LEDs based on the selected status of the DIP switches. Running this part of the code achieves the same functionality as the Vitis C code we developed in the previous video. The program reads the DIP switch inputs in polling mode. This means the system continuously checks for input changes in a loop and applies corresponding adjustments. Let's run the code and see the results running on the board. Flipping the first switch changes the LED shift direction. The second switch slows down the LED shifting. The third switch pauses the shifting. The fourth switch turns off all LEDs.